And Dipankar for inviting me here. I saw Professor Leggett just about 24 years ago during a StatFizz meeting in 1994. I was just about to start my PhD with Arup at that time, and I had absolutely no courage to go and talk to him at that stage. But it's 24 years later, here I am, and I'm delighted to be here and trying to connect to the computer to give the lecture on something which is, I would say, peripherally connected to, although there are so many different areas that one could talk about here, but I thought I should try this one, which sort of has some kind of connection to superfluidity of science, and which is here. I'm sure Professor Leggett has visited IISc a few times before. I don't know, how many times have you seen IISc? Three or four times? Okay, excellent. Okay. I have a lab there which works on the two-dimensional materials of different form. It's something which does its own material engineering. What I mean by that is that it looks at physics or tries to emulate certain physics by using two-dimensional layered solids, which are quite interesting material these days, and we expertise in low-temperature transport and so on and so forth. So the 2D family as such is a very large family. It's expanding every day, and we know about 30 of them at this point of time. But it looks like from the recent work, which is, came out in Nature Nanotechnology earlier last year, that probably we're at the tip of the iceberg. From independent evaluations of chemically independent compounds, there are probably about 1,825 layered solids that should, in principle, one should be able to exfoliate in two-dimensional layers. By exfoliate, I mean, for those who the talks I heard, it's a really varied audience. By exfoliation, I mean to say you take a tape and then you take out each and every molecular layers using simple peeling methods. Okay, so that's one of the major ways in which these kind of compounds are being created today. My group actually looks at one step farther than that, and what we want to do is that we create heterostructures of these kind of molecules, this kind of layers, and stack them one after the other to serve our own purposes. And I'm going to explain what one can do with it. Let me see if this video works. Oh, it might work. Excellent, thank you. So this is essentially how we make these van der Waals heterostructures. We exfoliate atomically thin layers, and then we essentially keep on sequentially pick up one layer after the other, and making heterostructures of different sequences made of different materials, different on different substrates, and so on and so forth. For example, if you look at this heterostructure, this has got a layer of two layers of graphene on top. This is black here, and the hexagonal crystal structure is a graphene. There's a layer of boron nitride. There's a layer of bilayer graphene. There's a layer of what is called a transition metal dichalcogenide, or TMDC, which is one of the major topics that I'm going to talk about today. Okay. What's interesting and where the physics comes into play is when you can make such heterostructures, you can actually create these structures with extremely clean interfacial property. And that can make charge go back and forth across the heterostructure. You can control it with a gate, you can control it with a bias, and so on and so forth. Okay? And that can lead to some very interesting properties, which I'm going to explain. I'm going to primarily explain with this one today, about 85% time. If I get time, now that I've lost a little bit of time, I might skip this one. Depends on how we go. Right, so what's interesting about that? making the heterostructures. You see, heterostructures have created very nice electronics background. I mean, what we can do, we can make extremely high quality electrical transistors where the electrical mobility of the charge is so high that it can actually cross the system from one end to the other without scattering even a single time. So ballistic heterostructures. Okay? So that's great. That's one of the very nice ways, but that has also created high quality material platform for realizing physics like what Janendra was talking about in the morning, for example, the fractional quantum Hall effect in these atomically thin layers, and Coulomb drag, metal insulator transitions, and so on and so forth. And recently, of course, by not just by heterostructuring, but also using layers with slightly different angles, one can go to superconductivity. And this has been one of the major discoveries in the last year or so, where by taking two graphene layers at an angle of 1.12 degrees, you can hybridize the layers in such a way that the hybrid becomes a superconductor at sufficiently low temperature. All right. But today's talk, is about optically excited van der Waals heterostructures. And let me tell you what I mean by that before we get into details of this experiment. First of all, the transition metal dichalcogenides are semiconductors, but they have a very special property. These materials can actually absorb light in a hugely efficient manner. That's primarily because right at the band gap there's a huge optical density of states which helps them to absorb nearly 30% of the optical radiation, even at when the layers are just one monolayer thick, maybe just 0.3 nanometer. So even one monolayer of these materials, of these chalcogenides, which is essentially chalcogen atom and sulfur or selenide or tellurium on the other side, they are extremely efficient light to electricity converters. Okay. But that's not the reason they are interesting today. That's not the only reason. So let's actually look at how a semiconductor material, once you shine light at them and create an exciton, what kind of structures that one can create to look at exciton condensation. This has been a work which has been going on for quite a while, particularly in the case of gallium arsenide, aluminum gallium arsenide quantum wells, where you apply electric field and you create, this is a quantum well, this is another quantum well, and you can create these kind of indirect excitons. The reason behind the indirect exciton is that now the electron and hole do not have the, they cannot fall on top of each other and vanish, but they form long-lived bound state, and this has been one of the major reasons of creating this biased double quantum well to look at the excitonic condensation process. It turns out that if you look at the number at which electron condensation can occur, the exciton condensation can occur is given by this, and because standard gallium arsenide, aluminum gallium arsenide heterostructures, here this is about 15 nanometer, the typical numbers of excitons is approximately 10 to the 10 centimeter per square centimeter. Masses are like this. Eventually plug this all in, it will give you a rough condensation temperature of 3 Kelvin or so. Okay. But this is where the transition metal dichalcogenides and the van der Waals heterostructuring can seriously change the scenario. For example, if I take a molybdenum diselenide and a tungsten diselenide, two different chalcogenides with different band gap, and I club them together, they come within about 1 nanometer of each other, which is approximately 15 times smaller than a standard gallium arsenide quantum well. And now they form in this type 2 heterostructure. This is the conduction band and conduction and valence band of tungsten diselenide, and this is that of the molybdenum diselenide. So now if I shine light on this structure, they forms what you call an indirect exciton. Okay? And if I now plug the same numbers in here, we rewrite this equation, and we find that in principle, one should be able to, particularly the Mott limit of exciton density, here because I can go to extremely high density of the exciton number, it's possible that the exciton condensation can occur at significantly higher temperature, probably close to 100 Kelvin or so. So the key aspect here is that we are able to get sufficiently close at the atomic distance or sub-nanometer distance where the two excitons interact extremely strongly. Okay? So that's the key reason. Right. Now, this has been realized in the sense, not the condensation part, but the fact that it forms an indirect exciton. This has been done in several groups over the last 4 years, and we now have even van der Waals heterostructures of such complexity in which the two semiconductor layers are these two, whereas here the insulating layers can be individual boron nitride layers that you can change the distance between these at will with today's van der Waals heterostructuring technologies. Okay? So this is a very potent and very versatile direction of research that's going on, but we wanted to ask a different question. We say that fine, instead of two semiconductors, can we use a graphene and the transition metal chalcogenide side by side? The distance between the two is about half a nanometer, and ask the question whether the transient optical state, which is essentially an electron here and the hole here, which is indirect exciton, can exist in such structures. Okay? The reason behind asking this question is because of extreme tunability of the structures to a metallic gate. I can apply electric field across it, I can change the Fermi energy here, and hence if I can create a transient structure which is the electron and hole in opposite layers, I can change its properties by simply electrostatically by using a gate from outside. So that's the purpose. Okay? This work has been done for a while now, and there are a lot of people, my students and my colleagues, have been involved in this. So this work had started about 5 years ago, and when we put graphene on chalcogenide and looked at electrical transport in graphene, it sort of gave us some very interesting results, because what we found is if I shine light on the molybdenum disulfide and measure the electrical transport through graphene layer, in dark, this is as a function of the gate voltage, where the gate is right here. It's in the dark, it's high current, and when I shine light, the current goes down, and from the ratio of the change in current divided by the power, it gives us extremely high what you call a responsivity. That is, typically a camera that you have in these computers or your mobile phone has got intrinsic responsivity of approximately 1 ampere per watt. This is about 10 orders of magnitude larger, which makes it one of the most sensitive photodetectors available today. It is the most sensitive, actually. Okay. After our work, actually, there are a large number of groups from different parts actually use this kind of heterostructuring and to obtain various forms of devices like light-emitting diode, like photovoltaic cells, and so on and so forth. We recently actually pushed this technique and made a single photon detector using graphene and molybdenum disulfide assembly as well. So these are device aspects, but let's not move into this. Let's ask the question now: how does an exciton breaks in and gives us the electricity? Because that's the core aspect of this, of all these device functionality as well as these heterostructures. See, the idea is when you shine light, the molybdenum disulfide, there's an exciton that forms. The hole is in the valence band and the conduction band, over here the electron. The moment they form, the electron essentially jumps out and goes into the graphene layer and conducts electricity. And it goes on conducting electricity for a very long time, because graphene and molybdenum disulfide are physically separated. The electron cannot jump back. And hence, the lifetime of these things, of these structures, are extremely long, about 1 second. The transport time along the graphene is very small, so that gives you a huge optical gain. So that's what gives electricity. Okay? But electricity comes because the electron is free. Okay? Whereas in case of exciton, electron forms a bound state with the hole inside the semiconductor. So natural question is to be asked is, even the binding energy of an exciton in TMDC, the molybdenum disulfide layer, is 0.3 to 0.4 eV, how does an exciton lead to free carriers? The free carriers are obvious, because the whole process comes from the exciton. You can see we measured the photocurrent in graphene as a function of the wavelength of light that I illuminate on it, and wherever the optical density of states are higher, that's where the photocurrent started getting up, becoming finite. Which means the origin of this phenomenon of photoconduction is from dissociation of exciton in the molybdenum disulfide layer. So, the light to electricity conversion. How does an exciton dissociate to free carriers at a van der Waals interface? So, let's look at the basic band diagram. This is the graphene, and this is the molybdenum disulfide. This is where the conduction band, this is where the excitonic state is, which is slightly about an energy EB below the conduction band minimum. When I shine light, I have electron and hole formation. This is where the electron goes. This is where the hole is. The moment they form, the electron finds this energy of graphene to be a lower energy state, so it jumps out and then goes here, and it gives it an ultra-fast adiabatic charge transfer, right? That's what we guess that should happen, and this is what happens in conventional semiconductor-based van der Waals heterostructure. So question is that is it very fast? Answer is yes. This particular transfer is, because it's a coherent transfer, it happens within a picosecond. This is the pump probe experiment that had been done by this particular group, and they showed that the electron transfer from the molybdenum disulfide, or here it is the tungsten disulfide, it goes into graphene within about a picosecond. The exciton splits within a picosecond, and electron is in graphene. That's fine, that's great. So in which case, one should ask the question that the electron, if it goes within 1 picosecond, and it takes about a nanosecond to cross the graphene, then the net, if I look at the current, then it should actually, from the light on, the current formation should not take more than a nanosecond. The answer to that question turned out to be particularly surprising. And this is a question. So suppose I look at the electrical current in the graphene layer, and I look at how long does it take to build the current after you shine light. And that turned out to be in the orders of tens and hundreds of seconds. But optically, the exciton breaks in 1 picosecond, the current transport occurs in 1 nanosecond. Where are 9 orders of magnitude of time gone? Is the question that we couldn't answer, understand for a very long time. We initially thought there are some dirt sitting in the middle, but those things were ruled out one by one. And more interestingly, when you increase the power that is incident on the molybdenum disulfide, you can see as I increase the power here, the speed at which the current goes to the final state becomes enormously fast. It's a power-dependent relaxation rate, which is also a very surprising result. Why should the rate or the speed at which my current is formed or electricity is formed after light comes in depend on how many photons I am shining on? Okay? And also, each and every of these relaxations as a function of time is a purely exponential relaxation. So what do we have here is that, so this exponential relaxation time tau is exactly proportional, the rate is proportional to the power of the optical radiation. So what do we have? We have a very slow exponential relaxation process. It's about 12 to 15 orders of magnitude slower than what we think an optical process should be. And finally, what is another interesting thing is it's persistent in nature. That means when I switch the light off, you can see the resistance that changed in the presence of light does not go back to the original value of the dark slit resistance. Okay. Now we started trying to understand this, and then we really didn't understand it for a long time. Then we asked the question, can we get a clue from another phenomenon that actually is extremely important to all of us, which is solar cells, semiconductor photovoltaics, and get some form of a lead from there. So we looked at the organic donor-acceptor complexes. Okay? And if you look at the donor-acceptor complexes, there are N and P, and there are excitons formed as soon as you shine light, and this then immediately dissociates with electron goes here, and hole remains on the P side. But you see, one of the mysteries of organic solar cells were that even in the charge transfer exciton state, the binding energy used to be about half an eV. And if that had been the case, there was no way we could actually separate them to get an electricity. But the solar cells work. Because you shine light, you get free carriers as electricity. Question was, how did we break the charge transfer exciton, even though their binding energy is significantly large compared to the room temperature, which is 25 millielectron volt. And the more or less accepted phenomenon is here that when this particular thing's formed, the hole is in the strongly localized state. And that hole essentially absorbs polarons and goes into a slightly higher energy, which is delocalized hole state. And when the hole delocalizes, it screens the electron-hole interaction, and that gives you the free electron, and that free electron conducts electricity. So the delocalization of hole seems to be the reason why a solar cell works in organic semiconductors. Another process can work here is that the charge transfer exciton can go back into the excitonic state, and that process is called exciton regeneration. So there are two processes that can happen. One is exciton regeneration from a charge transfer exciton, and the second is hole delocalization that leads to a free carrier in the system. So the question that we ask is, are these the processes? Because right now we have this process and we have this one, we have got free carriers. We do not know whether this particular intermediate state is happening in our van der Waals heterostructure. Okay, so this is the current knowledge that we had, and I'm going to add our understanding to this knowledge. This is the optically excited van der Waals heterostructure. There's an exciton that has formed within the transition metal dichalcogenide layer. The graphene layer is neutral. And then to get the electric current, I have got the hole remaining here, and the electron is at the Fermi energy of the transition metal of the graphene layer. What I'm saying, there's an intermediate state. An intermediate state is what you call a charge transfer state, and the difference between the intermediate state and the final state is that the nature of the wave function of the hole that's there. So this is a strongly localized hole, and this is a delocalized hole, which has come through the emission of interface phonons. So the overall energy scale, energy diagram will be that this is the highest energy state, which is the electron over here, and we have the lowest energy state, which is, of course, lowest energy state is the photon is absent. I'm discarding that out at this point. But this is the charge separated state, which is essentially the free electron in graphene layer and a delocalized hole in the transition metal dichalcogenide layer. An intermediate state where the electron is in the Fermi energy of the graphene and the localized hole. So the difference between the two energy state is approximately h bar squared over 2mz squared, where z is the localization length of a typical exciton in the chalcogenide layer. And this energy difference is approximately 85 millielectron volt. So is this hypothesis correct? Let us have a look at it. So because there are two possibilities here. One possibility is that this particular state can now send some electron back into the excitonic state, exactly like what happened in the organic solar cells. I can have what you call an incoherent back transfer of charge. That means now this particular graphene is accumulating electrons by two processes. One is you dissociate the whole exciton here, the electrons have come, which is given by the number of electrons which are here, which is the number of electrons that has been formed in the graphene after dissociation of holes, exciton here, minus, that is the amount of charge that is going back, which is given by a rate. That this rate is essentially proportional to the number of available exciton state or the whole state in the chalcogen layer. And that has two aspects. One is it is directly proportional to the optical density of states in the chalcogen layer and the energy difference between the Fermi energy and the excitonic state energy. So these two parameters will determine the speed at which the electron can be back transferred into the chalcogen layer. But very importantly, these are incoherent tunneling events, and hence this can be exponentially long. This can be in the orders of seconds that we have seen in the experiments. So to prove this, first we looked at the transition metal, how the transfer rate depends on the optical density of states. You can see these are experimentally obtained data that the tau inverse is exactly following the photoluminescence of the chalcogen and chalcogen layer, showing that this rate is directly proportional to the optical density of states. That's number one. The second point is it dependent exponentially on the energy difference between the Fermi energy and the excitonic state? Answer to that question is also correct. You can see that as the Fermi energy is changed as you go up, the closer and closer to this particular state, the rate increases dramatically, and almost diverging at a specific point. And that's when we see that the Fermi energy is essentially at resonance with the excitonic state. And from that calculation, from here to here, I have calculated approximately 105 millielectron volt. That gives us beautifully the binding energy from these numbers, the binding energy which comes out to be exactly the correct binding energy of excitons in chalcogen layers. Okay. Finally, is this energy scale also meaningful? That is a delocalization time. As you can see that when you are at a very high temperature, now electrons can actually get thermally activated to this particular state, and from there they can tunnel across and disappear from the system. As a result, the number of charge in graphene decreases very fast in an activated manner with an activation energy of 80 millielectron volt, exactly the delocalization energy. Yeah? 1 minute or 2 minutes? 2 minutes. Excellent. Yeah. So this is the final. This is the present situation. We now have found, I believe, that there is an additional state which is a charge transfer state when the electron is in graphene and the hole is in the chalcogen layer, where the whole wave function is a localized wave function, which is a high energy state here. And it's exciting for us because this intermediate state can actually be tuned with energy and leading to a gate tunable quantum two-state system. One could probably use it for a different purpose altogether, but understanding this intermediate state was particularly essential in a hybrid of this sort. Now, I think I'm going to skip this part because today, I lost some time initially, but we did look at this is what I had, another example of charge transfer which leads to a very interesting thermoelectric transport in such bilayers of graphene, but where the hybridization of charge and phonons leads to a very interesting layer and twist dependent thermoelectric properties. I'm not going to say this at all, but because of our ability to make heterostructures, we can make these kind of graphene bilayers, in which you can get access to two layers which are separated by 0.3 to 0.5 nanometer, and you can look at electrical transport across these structures. And if you do that, and we find something very interesting, that if we heat up one layer and look at the corresponding voltage difference, which is the Seebeck coefficient across 0.3 to 3 to 5 angstroms, it depends extremely strongly on the angle of individual graphene lattices between different lattice orientations. For example, this is a Seebeck coefficient temperature dependence at large angle, where you can see instead of the directly proportional to temperature what the Mott relation predicts it should be, it actually is a very flat and it saturates at high temperature, and it can be entirely explained by electron-phonon interaction at the two layers. And higher the number of phonons, it kicks the electrons out and creates a voltage difference between the two layers, and the Seebeck coefficient is described by the derivative of the Bose-Einstein distribution. And if you go to a lower angle where the two are strongly coupled, you can see this is highly Mott type distribution. You can get the Mott relation back when you change the hybridization by changing the angle between the temperature between the two layers. Anyway, I will not, this is my last slide. You can see depends on the angle, what happens to thermoelectric figure of merit as a function of temperature. This is more or less this is the summary. What we have shown is that, the van der Waals heterostructures can be used as exciton source and look at possibilities of looking at superfluidity in exciton condensates at high temperature in the order of hundreds of Kelvin. We have asked the question whether a graphene TMDC heterostructure can host such excitons, and answer to that question is probably yes. And apart from that, there are new possibilities of charge transfer that can lead to very unique lattice orientation dependent thermoelectric phenomenon in these kind of hybrids. Thank you. Yeah, Jayendra.
So you mentioned excitonic superfluidity. How did they see it? By counterflow experiment?
No. At this point of time, excitonic superfluidity is probably be seen through very strong photoluminescence. So this is one of the reasons why we want to enter this particular direction. All excitonic superfluidity basic material platform are two semiconductor heterostructures. One is molybdenum disulfide, other is tungsten diselenide, or whatever it is. So their electrical transport means nothing, and contraflow experiment simply cannot be done.
Why not?
Because they are extremely difficult to get proper mobility of charge. Electrical mobility is so small, contact resistance is so large, it becomes particularly difficult. So the only way you can see is extremely high enhancement in the photoluminescence, which has not been observed so far yet. Okay? But there's a lot of group which is trying this today. So one of the reasons we wanted to enter this is because if I convert one of the layer to graphene, which is a metallic system, I can actually now do these counterflow experiments, or at least try to see if there is a anomaly in the charge transport at a certain value of the exciton density. We should be able to detect it easier.